So hi everyone, good morning. This is work that I have done with my co-authors here. This work was started at the U.S. Naval Research Laboratory. I'm no longer at the U.S. Naval Research Laboratory. I'm now at Parallax Advanced Research. And then just a disclaimer that the views and opinions here are not reflective of the views of the U.S. government. Okay, so this is what I'm going to talk about today. I'm going to talk about the research problem. I'm going to introduce this one of the main notions of the paper, which is this lifted linked clause. So this is what we use as goals to the exploration planner to drive the agent to go collect examples to do learning. Then I'll talk about that exploration planner and the process. And then I'll show some early empirical results that we compare against some baselines. Still more empirical results we need to do. And then I will talk about, I'll kind of wrap things up. So the motivation is we're looking at developing agents that are capable of learning in unknown environments. In this case, the focus is on action models. So an agent that doesn't know necessarily when it can take an action and when an action will do something and what it will do after it takes it. And then we also want to see if we can have a planning agent that can kind of plan to go to a new situation to then do learning. So assumptions underlying this, we don't assume the agent has to have a goal given to it by a human or anything else. But we want an agent that can be goal directed. So we do expect at some point, we'd like the agent to be able to achieve goals given to it. We don't require that it has a complete action model. Actually, in the experiments, the empirical results that I'll show, we start off with an action model where for every action, there's no preconditions and no effects. And then there's no reward in the situation. So there's no reward from the environment that the agent gets. We are, for this work right now, we're assuming a symbolic, this work is using a symbolic state representation that is relational. So I'm going to use some examples to just ground the notion of what an LLC is. So I'm going to just borrow some of them from this game, Dungeon Crawl Stone Soup. You don't have to know many details about this to understand. I'm just going to lightly touch on it. But basically, this is a grid world-like domain where there's a lot of different things happening, and there's kind of a rich, interesting action space. This is currently an unsolved challenge problem in AI. These roguelike video games have gotten interest recently, and in the last couple of years, there's been some APIs in the last year and a half, really, there's become some APIs to do AI research in these now. So if you're at all curious, you can find some more details there or ping me after. So for real world domains, they may not be fully modeled. They may change over time, open world novelty, and also for some task achievements, it's going to be really important to maintain an accurate action model. This is kind of the motivation driving this problem. Now, this work is related to intrinsic reinforcement learning. So there's some approaches by Hester and Stone and others. There's been work on this for a period of time. The idea here is that the agent would get a reward for, say, taking an action that it's never taken in a current state, or by obtaining a new transition. So from some state, it's able to transition to a state that it's never transitioned to from that previous state. It would then get a reward. And then there's been some work looking at intrinsic motivations that are based on appraisal dimensions from work on emotions. And so, for example, novelty here is related to the proportion of an action being taken in a state, where if an action hasn't been taken very much in a state, they would have higher novelty. So one of the main differences from intrinsic reinforcement learning agent, here we're considering a goal-directed agent. And there's been, so in this work, we're using inductive learning to actually learn the action models. There's been a long history of work on this. Actually, there's been some other talks here at ACS about inductive learning. So for the inductive learning that we are doing, we are using an off-the-shelf tool. We're using ILASP, which I'll go into a little bit more detail in a bit. And one of the main things here is that, so some of the past work on inductive learning kind of assumed you would have some expert traces given to the system, and then you would learn an action model. Here, the agent is itself trying to go gather those basically examples that it would then learn from, and how can we guide that process of the agent going to get examples. So outline, now I'm going to focus on lifted linked clauses and what these are. Before I do so, I want to just, I think some folks are familiar with this. This is kind of an example of an action model that actually we had developed at one point for the Dungeon Crawl Stone Soup domain. And you can see it has preconditions and effects. So this is an action for moving north. And as long as there's not these types of obstacles, and there is a cell north of the agent, then the effect would be at the bottom here that the player would no longer be in its current cell and now would be in its destination cell. So a lifted linked clause is, we define it as a lifted subset of predicates of a state space where those predicates share at least one variable across their arguments. So it's a first order relational conjunct, and it has one or more existentially quantified variables that is satisfied by some states in the environment. And we will say that an LLC is active if it currently unifies with the current state. And the reason for having the one or more existentially quantified variables is just to have predicates that are related to one another. So we want to avoid, we think it's a good idea to avoid, for example, if you're in the bottom left corner of the map and there's like a wall in the top right corner, and there's really no variable like coordinate or anything else that's relating those two things, they're probably not very related. So that's kind of that intuition behind that. So I'm going to go through some examples of what lifted link clauses look like. And the generality of them is really what we are using to try to make the exploration of the agent a little more efficient. So so at the bottom here, this is what a player just would look like on a tile in Dungeon Crawl Stone Soup. And there are these shafts that an agent can fall through. And so this is what it looks like with the agent on the shaft. It might be a little hard to see, but there's some gray background here behind this. And so the actual state example here might be that the agent's at some XY position 5-7, where this tile is, and there's also a shaft here. The LLC for this would be this, but except we have lifted variables here. And note that for all variables here, they're shared across both of these predicates. And we would say this is an LLC of size 2. And size is something that I'll mention later. So another example is that an agent is in front of a closed door to the north of it. So we might say that, or the symbolic state for this specific example would be the agent is at coordinate 5-2. There's a door at 5-3, and 3 is north of 2. And this would be the LLC that captures the situation. And so the idea is, because we have variables here that are, and they're connected across these, we're describing all situations, no matter specific state, where the agent has a closed door that is north of it. And then just one final example to is if we had a monster left of we had a monster west of the agent, this might be the exact symbolic state, and this is what the LLC would look like. So for any given state, there are often multiple LLCs that are active. So because of what's happening in this orange box here, this LLC would be active where there's a monster east of the agent. We would also say that there's a monster northeast of the agent. This could be another LLC. This is an LLC of size 4. And then there's an open tile west of the agent, and we would say this is another LLC. So now I'm going to talk about the exploration process and how we use these LLCs. So this is the agent architecture for what we have in this system. And so we treat the environment as a black box. The agent sends actions to the environment, gets states back. These actions and states are also recorded into this interaction history. And then using the interaction history, we call a transition model learner, which in this case is ILASP. And this will basically update our domain model, which is then used by the planner. So the interaction history is a collection of every transition experienced by the agent so far. And so these are state, action, state pairs. And this is every time the agent tries an action. So even if actions fail, they'll still be collected here. The domain model has the preconditions and effects for every action. And then we're using ILASP to do the transition model learner. So more detail on that. To learn preconditions, we use ILASP. And what we do is we take these transitions and we label them as positive or negative. Positive examples are ones where the state changed, and negative examples, we consider that when an action failed and there's no change in the state. To learn effects, we are just performing a state difference between the previous state and the post state to see what changed. So now for the controller is managing what LLCs are active. So that's something that's kind of always being tracked, is which LLCs are currently active in this state and which actions have we taken in which LLCs that have been active. So if we're in an LLC where we haven't taken an action before in this state, we'll take that action. Otherwise, we will attempt to call the exploration planner. Now, there are some situations where the exploration planner will fail. One example is just when the domain model has the actions have no preconditions or effects. And then if it does fail, sometimes we're just forced to take a random action. Now, the purpose of the exploration planner is to reach new states where there are LLCs active where we haven't tried actions while that LLC has been active. And when a plan is executed, it either succeeds or fails, because especially in the beginning, as time goes on, the domain model might have a lot of inaccuracies to it. So what happens is, let's say it's inaccurate, but we're still able to generate a plan. It's just that when we go to execute that plan, it may fail. Well, that's fantastic, because now we've collected a negative transition, which is almost always going to mean we're going to be able to update our domain model. If the plan succeeds, well, that's great too, because now we're in a state where there's some LLC that's active that we haven't been in before. Perhaps now we're in front of a closed door and we haven't been in front of a closed door before. And now we can try actions to see if there's a new action we can take because we're in front of a closed door. So the way that the exploration planner working is it's tracking the actions that have been taken in which LLCs in the past. And it basically sorts the LLCs by the ones that have had actions taken the least. And so it will start to basically go through that and choose an LLC to be a goal, and it'll call the exploration planner. Now, even though it may choose an LLC to be a goal, it may not be able to generate a plan. And so we will keep trying until we're able to generate a plan. Now, the actual planner that we use, we use an answer set programming planner that's kind of just a straightforward implementation. And the nice thing is that we can give the LLC as a goal directly. We don't have to ground it into concrete states. So if our LLC is to be in front of a closed door, the first or the closest state that when we try planning where we're in front of a closed door that hits, we'll just end up taking that one. So now I'm going to walk through a little bit of example. This is one of the scenarios we used in the empirical results. So we have this 5x9 little grid world. The agent is here in the bottom left corner. There's walls here, there's walls here, and there's a closed door over here. The agent has actions to move in all 8 coordinate directions and diagonals and north, south, east, west. And then there's also 8 actions for opening a door in those directions and for closing an open door in those directions. So there's 24 actions here. So basically the agent will start here, and it'll try a bunch of random actions because it has no action model. And let's say after 15, one of the random actions is the move east action, which works. And now the system has learned a partial precondition that if there's a cell east of, if there's a coordinate east of the agent, then the agent will be able to move there. And so at this point, there's still some LLCs that are active that we haven't tried before. We haven't tried taking actions. So there's still some local exploration we're doing. So agent keeps trying actions, and then it ends up trying the move west action, and it goes back to this. So, and now it's learned a partial model for moving west, and it gets to this state, and then it's back in this state, and it's tried all available actions for all the LLCs that are active here. And so at this point, it triggers exploratory planning. And so what happens is, among all of the LLCs, we just end up choosing an LLC where the agent is at an X coordinate that is shared with a closed door predicate. So what does that look like in this state? Any of these tiles would be states where this LLC is active. And so this is given as a goal to the exploration planner. And then the exploration planner, because it hasn't yet learned anything about walls and whether or not I can move through them, it generates this plan. And then it will start executing this plan. So the agent starts moving, it gets here, and then this action fails. And when it fails to execute this action, it's collected a negative transition for the move east action. And so it's now able to update its domain model, its preconditions, that there cannot be a wall when it wants to move east. So that's how the exploration works. I'm now going to move on to the empirical results we did against the baseline agents. So we started this with a domain model that has no preconditions and effects. We did specify kind of the action signatures and the predicates, so the arguments that would go into the actions. There are 24 actions here, the 8 cardinal directions, and then there's 8 of these to open or close a door in the corresponding direction. The scenarios are static and fully observable. There is this pre-processing step where essentially we generate all LLCs up to a certain size. We do this with the domain file that we have for the environment. So there is the assumption here that the agent has predicates about the current environment. And then we have 3 agents. We have a random agent that just always takes random actions. We have an explore local agent. So what this agent is doing is it's tracking which actions have been taken for which LLCs have been active, but there's no planning. So it's we think it's slightly better in terms of, instead of taking random actions, it's going to take actions it hasn't taken in this specific context, but otherwise there's no consideration of taking actions farther than one step ahead, basically. And then planning, when the LLCs have not been exhaustively tried for the 24 actions, it's going to follow the policy of explore local. But when that is reached, it's going to attempt planning to try to reach a state with an active LLC for which it's never been in. So these are the 2 scenarios we've done so far. This scenario 1 I already went through. Scenario 2, so scenario 1 has kind of a maze-like style. If you see, there's really only one possible action that will succeed in the beginning, and then the agent kind of has to be kind of directed to get out of here. Taking random actions, this would take a really long time if it ever happens to get out. Over here, it's a little bit less of a maze-like structure. The agent has 2 choices to begin with. There is a closed door here, and there's some walls scattered throughout. Also, scenario 2 is a bit smaller in terms of the number of tiles. So the hypotheses that we have for these 3 agents in these environments is, 1, that all agents will be able to learn some action preconditions from the collected interactions. We think the second hypothesis is that the explore local agent will learn better preconditions for more actions than the baseline agent. The third one is that the explore local agent will visit more of its environment than the random baseline agent. The fourth hypothesis is that the planning agent will learn a better precondition model for the explore local agent and the random baseline. And the fifth hypothesis is that the planning agent will also visit more of its environment than the other two agents. So these are the results of how much of the environment the agent visits in the trials. So these are run up to 4,000 actions. We did 3 trials for each agent, and everything is happening online. So the agent takes an action, and if it gains interactions, it'll call a transition model learner, and it'll learn a domain model, right there in the middle of while it's acting. And on the y-axis here is the number of unique tiles visited. So kind of the cap here for scenario 1 was 5 by 9 tiles. So little bit, so it doesn't fully explore every tile, but it does visit a significant number of them. So what we're seeing here from the behavior is that the planning agent, the heavy line here in the middle is the average across the 3, and the shaded area is showing the minimum and maximum. So, in one scenario, the planning agent was able to jump way ahead very quickly. In others, it had to try a little longer, but eventually it does catch up here and eventually get up here. The random and explore local agent, we thought the explore local agent might do a little better, but it turns out it's not too much better than it starts to pick up ahead a little bit here, but otherwise it's pretty similar to the random agent. Now for scenario 2, because there's more starting options in the beginning, kind of all agents pick up a little faster, but still we see kind of a similar thing where the planning agent is able to kind of move ahead much quickly and visit new tiles. So these 2 results right here, I will just say, are kind of an indicator of how many different states in the environment the agent has visited. And the reason why looking at this is informative is because there is the general idea that by visiting more states, we'll have collected more unique interactions to learn a better action model. Okay, so now we want to look at the actual model that was learned and how good is the model. And so for this, we wanted to be careful with our evaluation. So we did not want to just compare the logical statements directly.
Yes, and you're almost out of time.
Oh, I'm almost out of time. Oh, sorry, I don't have my clock. Okay, I will just quickly speed up. So I'll just take 1 more minute, I think. So we did a careful evaluation. Instead of just comparing rules directly, we constructed these test states, and we basically tried perfect action models that are hand constructed by a user in all of these, and basically tracked if the action could be taken or couldn't be taken. And then we did the same thing for the learned models, and we used this to construct F1 scores. And so what we see here is that Explore Local was able to learn better action model, more of an action model than random, and planning was able to learn even better. But even in the 4,000 actions, it didn't learn everything. And similar results here for the planning agent. And then to wrap up, and those are that's in the paper if you want to look at that more closely. So basically, strong evidence for hypotheses 1 and 5 that all agents were able to learn some action preconditions, and the planning agent very much did explore more of its environment. H2 through H4, there was support for these. They weren't strictly true, however. But in some cases, they were kind of mostly true. And so we did see the planning agent, it helped. So kind of just to wrap up, we introduced LLCs as a potential approach to representing contexts or situations that could be used as goals to guide an exploration planner. Depending on, so these examples were kind of small. There is a little bit of a scaling issue depending on your representation, how big the domain is. However, we still think small LLCs are very useful. In this work, we had LLCs up to a size 2 that we used. And there's many exciting avenues for future work. And at this point, I will stop for questions. I just also want to say one last thing. At Parallax, we do have positions that are open and working to hire for multiple positions. So just a shameless plug. We're interested in cognitive systems people.
Okay, thank you, Dustin. There's a lot of questions on the Slack channel this time.
Okay.
So why don't we try to let people ask? Well, all right, I'll read Mohan's. The first one is from Mohan Sitaran.
I can speak if you want me to.
Go ahead. Go ahead.
So I'll paraphrase probably and combine them. So Justin, probably to comment / question together. So I presume you have to give, from my understanding of just looking at your paper, some prior knowledge of the domain in terms of the set of states and actions and the structure of the models, right, for the LLC and otherwise. Otherwise, it cannot learn. So given this, can you talk about how this use of this LLC is different from, say, encoding this using some logic rules with variables, and then that's methods that support lifted inference and grounding?
Dustin, can I help?
Sure. Yeah, please go ahead.
They are not different from logical statements with variables and inference. We are using the term lifted linked clause specifically to refer to logical clauses which have variables shared among them. Lifted meaning variables and linked meaning the variables are shared.
So I'm probably not. So the use of the lift LLC is not what is the key thing here. It's the use of them to do exploration then? I'm missing something.
So I think the idea is to use them basically to represent. So you could just say, I'm going to keep track of all possible states, and I'll just somehow try and sample the state space and pick a state as a goal to try to plan to reach at any point in time. I think that's going to be very much intractable. So instead, by using something like LLCs, you're basically saying, well, we really only care about contexts that are general in this way. So as long as I'm in front of a closed door one place, that's fine. So in that way, it kind of shortens the state space, and yeah, I guess that's one of the benefits of it.
Okay. Thank you, Justin. So Justin, sorry, I'll continue this separately. Thanks. Yeah.
Mike, you want to ask your question?
Sure. So are you assuming that there's no exogenous events or other agents that are doing things to change the world at the same time that you're doing something?
So we really want to get to there. So we're excited. We have a lot of interest in continuing this work, and this is kind of the first part of it.
Okay.
And so, yeah, basically, yeah, dynamic environments is absolutely, and other agents is a, yeah.
One of the keys for your decisions was the fact that when you did an action and there was no change of state. So that's one, it could be another agent, but you could also have some operator that has multiple effects, and the state that didn't change, you don't know, there is some other effect that occurred. When you have multiple effects, are you assuming only one effect to be able to do this or not?
No, we're not assuming only one effect. No, there can be multiple effects. Yeah, so basically, to tackle, we have some ideas on how to tackle that issue. Right, so if there's other agents, or if there's actions that have different multiple options for effects, maybe it's probabilistic in some way. We might be able to do things to extend the learning component and the representation of the action models and things like that.
Thank you.
Yeah, I guess we could do one more.
We're probably out of time, but
Yeah.
do take a look at Scott Benson's thesis, and because I think it's probably even more relevant than Mei Wang's thesis, which I know you know about. And I can follow up separately, but I do want to understand better where the the LLCs come from, and why you couldn't, why not generate new LLCs as you learn the conditions on the actions? Why not make
Yes.
those new
So,
LLCs?
Pat, absolutely. So yeah, we have ideas for that as well. The other thing I want to say is, so I very, even maybe just on this slide I touched on it. There's some scaling issues, but I think this is also a place where there are certain heuristics, or even if you had common sense knowledge, those could help reduce the space. But yeah, Pat, like if you have some idea that certain actions are similar, like maybe you somehow have some idea that all movement actions are similar, and one movement action fails when there's a wall, maybe you could extrapolate that to all movement actions might fail if there's a wall. So I don't know if that's exactly what you were saying, but and I'll end there. So, and I'll check out the Slack to respond further.
Great. Thank you, Dustin.